Welcome, ladies and gentlemen. Let's go ahead and take a look at our Bellwork for the day. And so we're done with our rules quiz, both symbolic and verbal, right? And you guys did a great job. Please check out Infinite Campus at your earliest convenience so you can see exactly how you've done the rules quiz. Let's go ahead and apply those rules now with straight differentiation. I know the derivative of inverse cosine is opposite of 1 over, and then the square root of 1 minus the input squared times the derivative of the input. It's just that my input isn't x, it's 1 minus 2x, and the derivative of my input is negative 2. So it looks to me like we could do a little bit of cleanup if we want to make that look a little bit better. I think I'll grab the negative times the negative is a positive. Oh, good catch. 2 over, and how do we want to make that bottom one? You want to FOIL that and combine like terms? So if we FOILed that out, we would get 1 minus 4x plus 4x squared. Is that what you guys got when you FOILed it out? Great. And then we'll go ahead and combine like terms. 1 minus 1 would be 0. And then opposite of negative 4x is positive 4x minus 4x squared. And then you went to look at the multiple choice selections, right, on the multiple choice portion of the exam. And this didn't show up as any of the choices, right? So what do? We could probably rearrange this a little bit further. Yeah, give up, quick, wantable.
Yeah.
What can we do to further simplify this? Riley?
You multiply by like a creative 1.
We could multiply by creative 1, but I'm seeing, right, these 4's are jumping out at me inside of a square root. And so something, right, a part of me wants to simplify that. We know that a radical does not apply across the sum or difference. But if I were to factor it and make a product, then I could apply the radical. You see what I'm saying? And so what's common to each of those terms inside? They each have a 4. And so if we're talking, and this is fine for right now, right? But if we're talking about selecting from a multiple choice response, yeah.
Should that be 4x minus 4x squared?
Oh, yes, 4x. Thank you. Absolutely. Thank you. Thank you. If we're talking multiple choice, right, and this response isn't here, I just want you to be aware that we could rearrange that into different forms so that there is, right, the response that we're looking for. And so what we're going to do, let's go ahead and factor out a 4, right, from each of those and rewrite 2 over. And I'm going to go ahead and pull that 4 out. And that would leave me with x minus x squared. Yes? And the only reason I didn't pull the x with that as the greatest common factor is because the x isn't going to reduce in the square root, but because this is now a product inside of a radical, I can apply the product property of radicals. I know that the square root of 4 times quantity x minus x squared is the square root of 4 times the square root of x minus x squared. Also that we can do what? Also that we can reduce. Look at that, 2 over 2 root x minus x squared. You guys see it? So finally, our response, hey, here's letter C. Oh, I was going to pick C anyhow. Right, most frequently occurring. Oh, well, now we generated it algebra. All right, what question do you guys have on number 1? Did everybody go all the way? Did everybody go all the way to the line? No. Did we get here? Yeah? No? Sydney?
So, for like one of our tests, we have to go to that last step? Or...
Not unless there were multiple choice. Right? Not unless there were multiple choice. Or the directions are simplified completely. Right? That's always the kicker.
Where could we stop then? Could we stop at any of those?
Yeah, I would want you to leave it like this. I don't want you to stop here. Are you okay? Yep. Good question. Other questions? Sydney?
Wait, so we can't, like, not to leave it at the first one where it's like the 2 parts, but like,
right.
We have to FOIL the 1 minus 2x. Do we need to do that? Or...
Not necessarily.
So
but I would not want you to leave it as negative 1 times negative 2.
Yeah.
I won't want you to leave it like that. Good. All right, let's take a look at number 2. Overall, what rule are you gonna use to attack number 2 overall? Grace?
Quotient.
Quotient. Good. Thank you. I see 2 functions of x. Right. With division, I know I'll be applying the quotient rule. The good news is that you guys memorized that. I know the derivative, right, of a quotient of 2 functions is the derivative of the top. And remember, cosecant goes to opposite cosecant x, cotangent x. times the bottom, that's e to the x, minus the top, that's cosecant of x, times the derivative of the bottom. Well, the derivative of b to the x is also e to the x. And I saw some of you with the factoring. That was cool, all over the denominator squared. All right, raise your hand if you had first step. So go ahead, first step. Can we simplify this one? Yes, certainly. What's common to the both terms in the numerator? What's common to each of those? Vivian? Absolutely. So we can factor that out. And if we were to factor that out, now we're noticing that common factor, I can do a negative e to the x, 1 or 2. Cosecant of x, cotangent of x, plus cosecant of x, all over e to the 2x or e to the exponent squared. Either way, it doesn't matter because now we can cancel out the common factor. So it looks like my final answer can be negative fraction. Uh-oh. We're going to fit this. Cosecant x, cotangent x, plus cosecant x, all over e to the x. If you chose to factor out the cosecant of x, that's fine too. If you left the negative inside on both terms on the numerator, that's fine too, right? All of them are equivalent, and you would not lose credit on a test if you stopped at a different, right, a different portion there. But you just don't want to leave it too early. Questions about that one? Raise your, oh, cotangent x. That would have been bad too. All right, so raise your hand if you got that. Can we get the equivalent? The equivalent? Yes? Okay. Overall words, right? What rule are we going to attack number 3 with? What rule are we going to use for that? Sophia? Exponential, good. The derivative of an exponential function is the exponential function itself times the derivative of the exponent, and cotangent differentiates to opposite cosecant squared times the natural log of the base. And there's not a lot of ways to make this look pretty, so however we want to do, I would definitely grab the negative and put it in front so that we don't confuse it with subtraction. Okay, we don't want that. But I would do negative cosecant squared, oh boy, x, ln 5, no, I don't know how to make it look good, times 5 to the cotangent x, but that c is not helping it at all. No. See if I can scooch in there. Oh, danger! Max and Ruby, danger, danger, red alert. All right, so we got the equivalent for number 3. Yay! Now we're winning. Now we're winning. Good job. Number 4, one of my favorite words. I'll tell you every time, just in case you forgot. Derivative inverse tangent, right, is 1 over 1 plus input squared times the derivative of the input. Input times the derivative of the input is what? Negative 3m squared. Is that what you guys are getting? Cool. So we can clean that up a little bit. So now I have a negative this time. Oh, we need a square now. How's that? Yes? Now we need a negative and a 3m squared. Awesome. And did you guys leave that or did you expand it? You expanded it? You left it?
That's pretty crazy.
That is pretty crazy. I'm going to expand it. I'm going to do, because I'm crazy, right, for one. And I rise to the challenge. I want a challenge. You know what I mean? So ready? 16 minus 8m cubed plus m to the 6th. How do we do? Yes? Combine like terms? Oh, so close. I'm getting 3m squared over 17 minus 8m cubed plus m to the 6th. And we could certainly put m to the 6th minus 8m cubed plus 17 is fine. We did see one like this on the AB free response, right, where they did simplify this to get to the final answer. Sophia?
Did you keep the negative?
Where did it go? Yes, I have to. Thank you. Good job. Yes. Crazy stuff. Good job. Awesome. So who got number 4? Did you get number 4? All right, and one tangent line to warm up for the day. Today, again, we're going to be working with applications to instantaneous rate of change, but with the new strategy, and that's included differentiation. So we need to be ready to go with our equation tangent line. You guys, should be great at finding the equation of a tangent line algebraically by now. You need the same three things. Guys, we need our same three things, our x coordinate of the point of tangency, which is usually given our y coordinate of the point of tangency. We have to find that in this case, and then the slope of the tangent line. So where do I go for the y coordinate? Into the original. Looks like -2. Squared is 4. Minus 2 times minus 2 is plus 4 is 8. Plus 3 is 11. Did you guys get 11? Awesome. And then where do I go to find my slope of the tangent line? Danny?
Derivative.
Good. So we'll do f prime. Thank you. And we'll generate our derivative expression, 2x minus 2. Then we'll evaluate it at my x coordinate of concern. And generate our slope of the tangent, which looks to be -4 minus 2 is -6. Raise your hand if you have slope -6, -6. We've got all the pieces. That's great news. So now if we be cheesy, we'll do y minus y sub 1 equals my slope m times the quantity x minus x sub 1. And if we wanted to, we could rearrange that. We don't have to. I'm going to get -6x minus 12 plus 11 looks like -1. Is that right? Raise your hand if you had the same equation. Right, number 5. Awesome. Okay, we can verify that graphically, but in the interest of time, I want to go ahead and keep going because I'm not sure how long our discussion will take today. So we'll go ahead and do our homework collection now, and I'll pause the recording. Okay, ladies and gentlemen, in the past we've seen how we can use, right, our differentiation to generate the instantaneous rate of change of a function anywhere along it, right? That's our derivative function equation, and we've spent the bulk of this unit, right, reminding ourselves how to find the slope of the tangent, and then using that to write an equation of the tangent line or an equation of the normal line, right? But finding the slope of the curve is the key importance. Well, let's consider a different type of relation. Is the current relation y squared plus 2 equals x, is that a typical function, y equals f of x, that we're used to seeing? Riley? No. What's different about this? Is y a function of x? No. We see that this fails the vertical line test, right? Anywhere to the right of x equals 2, a vertical line would cross the relation more than one time, meaning that a given input x is paired with multiple outputs, one here down here in the negatives and one here in the positives. And so this is not y is a function of x. This is an implicit relation where we've got not y solved for, right? Y is not solved for a formula in terms of x. In fact, this is called an implicit relation. And so we've got a couple different options here. We could certainly solve this particular relation for y, and then use whichever side of my relation this point is on, differentiate it, and generate the slope of the tangent. However, a much easier way is to leave the curve as is, with x's and y's mixed up on the same side, y not solved for as a formula of x, and then differentiate right now using the chain rule. So that's why we did our practice with the chain rule. That technique is called implicit differentiation. It allows us to leave our x's and y's mixed up. We don't have to have our relation solved for y. And now we can differentiate term by term. We'll just, every time we differentiate a term that includes a y, we have to include times the derivative of the base, which is dy dx. That is the derivative of y with respect to x in accordance with the chain rule. So let's go ahead and differentiate this term by term, and then we can do a quick check. So here we go. I know that I still need the same three things. I need the x coordinate point of tangency from Bellwork, given. I need the y coordinate point of tangency, just like Bellwork, given. The only difference is I need the slope of the tangent line. That's still dy dx. But to generate it, I'll use implicit differentiation because I got x's and y's mixed up. That is, y is not solved for as a formula of x. So how do we do that? Easy. We differentiate term by term. The derivative of y squared with respect to x is 2y exponent times the base raised to the 1 less times the derivative of the base. And more frequently, I'm seeing dy dx used as the notation in this text, not the y prime, and so I'm going to go ahead and try to be consistent with that as well. The dy dx, that signifies the derivative of y with respect to x, the first derivative of y with respect to x, which is y prime, which we've seen in the past, plus the derivative of 2 is 0, equals the derivative of x is 1. In one step, we can generate an expression for dy dx, the instantaneous rate of change in the relation with respect to x, right? By using the chain rule and implicit differentiation. Solving for dy dx gives me an expression that, by golly, now will allow me to get the slope anywhere along that relation simply by plugging in the y-coordinate. Look at that. My derivative is based on the y-coordinate, and that makes sense, right? Depending upon where I look, if I try to put in x equals 3 into a derivative equation, there's two different places. However, here, there's only one place where the y-coordinate is -1, and so this is more quick and efficient. So now we'll evaluate my dy dx. The instantaneous rate of change of y with respect to x at the x value, the y value, -1. And that's 1 over 2 times -1. And that's what? -1/2. You guys getting -1/2? Sweet! And then the rest is the same. So I'll go over, guys, and we'll do a quick check in the graph. I'm going to do y minus y1 equals m times quantity x minus x of 1. So I get y equals -1/2 x. Negative times a negative is positive 3/2, minus 2/2 is plus 1/2. All right, I'm going to go ahead and use the graphing calculator to check. And so what I want to do is see if our equation matches up and forms a change to that. However, in order to enter this relation into my graphing calculator, I can't enter y squared plus 2 equals x. I'm going to have to solve for y and enter my calculator. No problem. And though I didn't get to it yesterday, we can do it quickly right now. I know my original y equals, if I were to solve that, would be the positive and negative square root of x minus 2. And so I'll quickly enter that now. The square root of x minus 2. Uh-oh. I don't need that though. And negative. All right, let's go ahead and make a similar window just so it looks snazzy. What did they do? -2 to 4. So they did -2 to 4. And they did what? -3 to 3. All right, so how do we do? There's the original relation. We'll go ahead and enter our tangent line, y equals, and I'm going to enter what we generated. We generated -1/2 x plus 1/2. Somebody says, oh, y4. Well, we get pink. That's cool. Hey, that's awesome. And then I can go ahead and do a quick check. With the second program, the draw feature. Again, 5. But this time I have to select the top curve. Am I on the top arc? No, so I've got to go down to y2, the red arc, the bottom arc, and I'm going to select the x-coordinate 3. Enter. And then you can see it traces over the line style and so it's done correctly. That's pretty sweet. All right. So for this first one, did we have to, right? Did we have to use implicit differentiation? No, we certainly could have solved this for y first, right? And then took a derivative. It's just then we would have two pieces, a positive and negative square root, and we would have had to differentiate with the radical. However, by leaving it as y squared plus 2 equals x, I only had to differentiate with the power rule with integer exponents, and that was a way easier derivative. And that's the power of implicit differentiation. In the interest of time, we're going to go ahead and skip possible power outage. We're going to skip this so we can get to the good stuff. So this is very similar, so I wanted to include plenty of examples in case we need more, but I think you guys are good with that. Instead, what we're going to do is focus our attention on more complicated implicit relations. And so imagine, right, if we were dealing with a relation like -x cubed plus 2xy plus y to the 5th equals y cubed. In fact, it's impossible to solve this for y as a function of x. And so that's where the power of implicit differentiation lies, being able to still find the slope of the curve anywhere along it, but when we're unable to solve for y versus this problem, we could have solved for y and just done a derivative with the square root. This one we can't, and so that's where we're going to focus our attention. I'd like to share with you the Folium de Descartes. And so Descartes is René Descartes, a famous mathematician who's credited with the Cartesian coordinate plane, the XY axis, and a variety of other contributions to the world of mathematics. In fact, he was a key player in the development of mathematics. This particular relation is not a function, right? This is called the Folium of Descartes. And what I want to do is go ahead and use it as a kickoff point, right, for more complicated implicit differentiation. So let's go ahead and take a look at this relation given by x cubed plus y cubed minus 3xy. Clearly, this is not a function y a function of x because it fails the vertical line test, right, there in that middle portion. However, we can still generate an equation of tangent lines, right, normal lines, etc., using what we know about dy dx, the first derivative of y with respect to x. So let's go ahead and verify first that what looks through inspection. Right about there, yes? Let's verify that 3 halves comma 3 halves is in fact on the relation. So what can we do? Well, we can simply plug in the value. So I'm going to go ahead and see if that's the case. So we want 3 halves, 3 halves. So 3 halves cubed is what? 27 eighths? Plus 27 eighths? Minus 27, bless you. Fourths? That's the beginning? Bless you. And what does that equal? Well, I'm going to leave this down here. And I'm getting 54 eighths. Oh. Minus 27 fourths. And isn't 54 eighths 27 fourths? So can we jump right to 0? All right. So that equals 0 as desired. Great. But what's more exciting is finding the right equation of a tangent line or a normal line or a line that fits the given constraints using what we know about derivatives. So let's go ahead and consider now finding there's my space, the equation of the tangent to the curve, right, at the given point. So I went ahead and included a little bit more space for you guys. Our goal here is to write an equation of the tangent line to the curve at that point, 3 halves comma 3 halves. So hopefully I've got a little more space. There I go. What are we going to do? X's and Y's mixed together on the same side of the equal sign. We'll use implicit differentiation. It would be very difficult to solve this for Y, though there is a cubic formula, although it's much more involved than our friendly quadratic formula. Okay, so here we go. Reti, derivative term by term. X cubed, differentiate with respect to x, is 3x squared. Plus y cubed, differentiated with respect to x, is exponent times the base raised to 1 less times the derivative of the base. The derivative of the base, y, with respect to x, is dy dx. So there's where we apply the chain rule. So everybody see that? Exponent times the base raised to 1 less times the derivative of the base. Then minus 3, and I'm going to go ahead and do the product rule for this. So for the product rule, right, for the product rule, I'm going to go ahead and focus in just on my x times y. The derivative of a product of two functions, x times y, is the derivative of the first times the second, plus the first times the derivative of the second. And there's my dy dx again. Everybody see that dy dx, the derivative of the second there? Equals, and what's the derivative of 0? Oh, that's still 0. All right, so we'll go ahead and get rid of parentheses so that we can hopefully group and combine like terms. We want to solve for dy dx to get the slope of the curve. In order to do so, we need to get a single dy dx isolated on one side, right, so that I can solve for it. So let's go ahead and distribute to get rid of parentheses. What do we want out of this whole mess? So we'll simply add or subtract to get all my terms of dy dx on one side, everything else on the other. So I'm going to leave this 3y squared dy dx minus 3x dy dx. And I'm going to go ahead and add over the y term and subtract over the x squared term. How's that? Great. Now we'll go ahead and factor out a dy dx so that I have a single dy dx isolated on the side as my goal at the end point. So notice how we have a dy dx in each of those. Factor that bad boy out, leaving with 3y squared minus 3x quantity equals 3y minus 3x squared. And guys, we're almost done. Now we can solve through division. So there's the fruit of our labor. Dy dx is going to be given by 3y minus 3x squared over 3y squared minus 3x. Notice how there's a 3 common to each of those terms. So factoring out a 3 on top, factoring out a 3 on bottom, dividing out 3 divided by 3 is just 1. Gives a simplified formula, it'll be easier to work with. How about y minus x squared over y squared minus x? Is that better? You got extensions on it for games. All right. How's that? Okay? Let's do it. So what do we need to do? We need the equation of our tangent line. So again, we'll go to our regular y minus y1 is equal to m. Where am I going to get my slope m? I'll evaluate this at my point of concern. So in order to get my slope m, I need to evaluate this at the 3 halves comma 3 halves. Can we do that? Certainly. I know that my slope of the curve, right, is given by y minus x squared over y squared minus x. So I'll simply replace the y and the x with 3 halves and evaluate. So can I do that upward shifting now? Alright, we'll do it right here. I get 3 halves minus 9/4 all over 9/4 minus 3 halves. So I get 6/4 minus 9/4 is negative 3/4. Over 9/4 minus 6/4 is positive 3/4, which means my slope after all that is what? -1. Could we have seen that even? It looks about, yeah. With the square window, it looks about. -1, looks about. All right, so let's finish it out. I get -1 times x minus 3 x. Awesome. Because I can't enter that in my calculator to make the picture, I'm going to solve this for y so we can see the y-intercept and see if we can visualize if this is a good equation or not. So I'm going to go ahead and finish this one out, you guys. Not all of it, but this one. Looks like negative x plus 3 halves plus 3 halves would be plus what? 6 halves, so that's plus 3. Is that right? So negative x plus 3. Can we visualize that? Let's see. So that's why I wanted to include the grid for you guys. So if we were to do negative x plus 3, here we have down 1 over 1, down 1 over 1, down 1 over 1. My super duper line tool. How do you do? 3 halves, 3 halves? Ha! Gosh darn it. Let's get nice. Make a screenshot of this. I love Google. All right. So what questions do you guys have about our implicit differentiation? All right, so what I want then is for us to practice and for you to show me that you get it. So let's go ahead and find the equation of the normal line to the given curve at -3, 2. Keep in mind this is the normal line, not the tangent line, the normal line. But I know with last night's assignment, you guys should be comfortable with doing an equation of the tangent line or the normal line. So do this with your partner. I'll pause the recording and we'll come together and check. Okay, ladies and gentlemen, so as we differentiate our implicit relation term by term, we're going to use the chain rule anytime we differentiate a y term, right? Because we're differentiating with respect to x, and y is a function of x. So here we go. 2x minus, and then I went ahead and chose to apply the product rule again in parentheses, so I want to make sure that I'm comfortable with that negative and distributing it after the fact. The derivative of the first times the second plus the first times the derivative of the second. There's my dy dx or my y prime, and then plus 2y y prime, again the chain rule, and then equals 0. So my general scheme for us is to go ahead and combine all the dy dx terms on one side, factor it out, and then solve by division. So let's go ahead and do that after distribution of the negative sign. I get negative y minus x dy dx plus 2y dy dx. And I'll go ahead and leave the dy dx terms on the left. I'm going to go ahead and scooch the 2y in front. And to the right, I'm going to add over that y and subtract over the 2x. Raise your hand if you got into the red line. So as you get to the red line with the dy dx is on the left, great. Now we can factor out the dy dx in a reverse distributive property problem. What's common to each of those terms on the left side of the equation? The dy dx, that's what we want isolated. So I'll factor that out and leaves me with 2y minus x closed equals y minus 2x. And now I can solve by division. So I'll go ahead and come over here. My dy dx is given by y minus 2x all over 2y minus x. Raise your hand if you generate dy dx solved for as a function of x and y. Yes, dy dx solved for. That's great. All we need to do is evaluate this expression, which gives me the instantaneous rate of change in y with respect to x anywhere along the curve at the point -3, 2. Do you see why we need this, both the x and y coordinate? Well, this ends up making an ellipse, and so it's not enough to say x equals -3 because there's two outputs when x equals -3. So we see that there's two outputs when x equals -3. One positive on this blue portion of the ellipse above the x-axis, and one on this negative on this bottom part of the ellipse, right, that is in the red portion of the graph on the line star. And so what are we going to do? We'll evaluate that expression. Here we go. I know that dy dx evaluated at -3, 2 is what? 2 plus 6 over 4 plus 3 is 8/7. Are you guys getting 8/7? Awesome. But we didn't want to write the equation of the tangent line. We wanted to write the equation of the normal line. So my equation of the normal line will be given by y minus y sub 1 is equal to m times quantity x minus x sub 1. And I'm going to use not 8/7, but -7/8, opposite reciprocal. So -7/8, and our point was plus 3. So x minus -3 is x plus a positive 3, and y minus 2. And I'm not gonna multiply through and combine like terms and run the risk of messing up with negatives and fractions, right? The F word in its first hour. So I'm just going to go ahead and leave this as -7/8 quantity x plus 3 plus 2. Also, I can put it in my grapher and see. So let's go ahead and put that in our grapher through inspection and see what we can see. So here we go. I've gone ahead and entered that relation, right, by breaking it up into a top branch of my ellipse and a bottom branch of my ellipse and entering them in my grapher. And now I'm going to go ahead and enter our generated equation by hand. We got -7/8 quantity x plus 3, close, plus 2. Yes? All right, moment of truth. I went ahead and added that, and we'll see how that does with our graph. And we're hoping to touch the curve at negative 1, 2, 3, comma 2. Does that look normal to the curve? It does not look normal to the curve. And so what do we do? Where do we mess up? I don't think we messed up at all. I think we can use our zoom square feature, which is pretty sweet. So I'm going to go ahead and do the zoom square feature so that it looks orthogonal to the curve. That is perpendicular. So I'll go ahead and zoom square, enter. And now, by golly, isn't that cool? That ellipse is pretty neat. Diagonal ellipse. Here it comes. Oh, very nice. And I'll finally do a trace. I'm going to go ahead and trace on the top curve. I want to trace a negative 3. And it looks like right there, there's our point, right, that we went through. There's our orthogonal or normal line to the curve. And I think that deserves a big tick. Hooray! Awesome. So what questions do you guys have about our implicit differentiation technique? The one thing we're going to have to do, and I noticed this on the AP exam in the past as well, is they've gone from not just the first derivative dy dx in applications with instantaneous rate of change, but they've gone to the second derivative. So I want to go ahead and add one more. This didn't make it to the printer last night when I was leaving before parent-teacher conferences, and so I went ahead and asked that you put it on the blank side and back. And so everybody flip to the back, we've got a blank space. I knew I wanted to do d2, a second derivative, but didn't get there. Everybody go. So we'll go to the blank. You guys have this one?
Yep.
Oh, not this one. This one. We already did the derivative of that, and so we don't need to, so we're skipping. I wanted to have more than less. Okay, so let's find the second derivative. Recall that our notation, Leibniz notation for second derivative, looks strange. This just refers to the second derivative of y with respect to x. And so we'll go ahead and practice now with our differentiation, but we're not going to stop at dy dx. We're going to go ahead and go to the second derivative. I'll still solve for dy dx in the first time, but it might involve a resubstitution. So let's go ahead and generate our second derivative. Again, term by term differentiation. Factorization of our common. A solve by division. Generates an expression for dy dx dividing out of 2 from all factors includes 2 over y plus 1. Is everybody good with our dy dx? Great, but the problem didn't ask for dy dx, it asked for the second derivative of y with respect to x. So I'm going to go ahead and import this dy dx and rewrite it. And how will I get the second derivative? I'll simply differentiate dy dx, the first derivative, to get to the second derivative. So what rule might I use to differentiate 1 over y plus 1? Well, I've got options. Because I have no function of y on top, I could use the power rule. Right? I wouldn't have to use the quotient rule. If you're comfortable applying the quotient rule, right, because we've got a fraction, then we could do the quotient rule as well. Which would you guys like to do? Power. So we'll go ahead and rewrite this as y plus 1 to the negative 1 rewritten. No derivative here, I just rewrote that. Agreed? Quantity to the negative 1. Now let's apply my power rule. Power rule, and I know so that's the real reason you want to use the power rule, so you can hear the little power wheels jingle. I don't blame you, because that's good stuff right there. The derivative of y with respect to x differentiated is d2y dx squared, that's the second derivative of y with respect to x, equals exponent times the base raised to 1 less times the derivative of the base. What, pray tell, is the derivative of the base? dy dx, and don't forget, otherwise it's not going to work out. We just differentiated an expression with y in it with respect to x. We have to use the chain rule. So dy dx is the derivative of y plus 1, my base. So that's why we're using the chain rule. Now let's rewrite this. For the second derivative, I'm getting negative dy dx over y plus 1 quantity squared. However, I have an expression for dy dx. right? What is the expression for dy dx? Oh, it's 1 over y plus 1. It's 1 over y plus 1. And so I'm going to substitute in my expression for dy dx. I'm going to substitute that in for dy dx. So I'll rewrite that as 1 over y plus 1 negative over y plus 1 squared. And that is the ugliest compound fraction I've seen in recent memory, so we'll go ahead and apply our rules for dividing with fractions. I know that 1 over y plus 1 divided by y plus 1 squared is the same as 1 over y plus 1 times the reciprocal times 1 over y plus 1 squared. However you'd like to simplify this, I get negative 1 over y plus 1 close quantity cubed. You guys see it? Bam! That's pretty sweet. If you don't like this, you could have left the dy dx here. And negative 1 over y plus 1 quantity squared times 1 over y plus 1 would be negative 1 over y plus 1 quantity cubed. All right, what will we label this? The second derivative of y with respect to x. And what about my original relation with d2y dx squared tell me? What information does the second derivative hold? What does that tell me about my original relation? Kobe? Oh, sorry, what is the second derivative give me information about the original relation?
Gives you the rate of change of the slope.
Right. So the rate of change of the slope visually, right? Visually, what is that? What feature about my graph is that? What's that called? Sophia? Yeah, the curvature, right? The curvature, the concavity, And so a y prime, or dy dx, tells me all about the slope of my original relation. Y double prime, or d2y dx squared, tells me about the shape of it, right? The curvature, the right side up bowl shape versus the upside down bowl shape, the concavity. And we'll have more about that next week. Excellent work, you guys. Okay, so I wanted to include some more implicit relations. Some of these can be solved for y, some of them can't be solved for y, but that's pretty cool. All right, let's close it up then. We've got back to the last page. I'd like a written response for each of these, and please be ready to share. What quality in an equation indicates it represents an implicit relation? That is, how can you recognize an implicit relation based on the original equation? Secondly, when is implicit differentiation then a better option, a better choice than traditional differentiation? Time. All right, so please share with the class when I call on you, what quality in an equation indicates you're dealing with an implicit relation? So for that first one, how can you tell that you're working with an implicit relation by looking at the equation? Emily?
Both x and y are on the same side of the equation.
Absolutely, we've got x's and y's mixed together, oftentimes on the same side of the equation. Y not solved for. So we've got x's and y's mixed together on the same side of the equation. No y equals, right? There's no y solved for as a formula. Great. So when then is implicit differentiation a better choice than traditional differentiation? Go ahead and share with the class. Sophia?
When solving for y is difficult.
Yeah, if solving for y to get y equals a formula for y is difficult or impossible. Or solving for y would create a harder differentiation problem than just leaving it as is, right? Because you introduce radicals or a more difficult rule. Awesome work, you guys. What questions do you guys have about your closure then? Okay, so on the back, underneath your d2y dx squared problem that you added, we've got our assignment then. Our assignment, I tried to select odd exercises so that you guys could check your answers from the back. And I'm gonna go ahead and do 54 and 56, the even exercises, and attach that as a key, so that you have the feedback still with the evens, but I'm counting on you guys to check the odd exercises in the back of the student tests. I'm gonna work on 54 and 56 right now, while you guys are working on the OTL, and you can get a jump on it. I just asked that you use AP Calculus time to work on AP Calculus. So I'll go ahead and pause and save the recording, and then I'm gonna work on the 54 and 56 right now, so you have that. Those are some neat problems. Great work today, you guys.